Hello, and welcome to Late Night Physics. If you're ready to dive into the wonders of the cosmos, make sure to hit that like button, subscribe, and don't forget to click the bell so you never miss a deep dive into the mysteries of the universe. I'd also love to know where you're watching or listening from tonight, whether you're tuning in from a bustling city, a quiet town, or somewhere out in the cosmos itself. I like to think we have some space explorers in the crowd. Now, tonight, we're about to embark on a journey into one of the greatest mysteries that modern physics is still trying to unravel: dark energy. You might be thinking, what exactly is dark energy? Well, it's a force so strange that it's driving the very expansion of the universe itself, but no one really knows what it is yet. It's the invisible force that seems to be pushing galaxies apart faster and faster. Yet, despite its power, it remains one of the most elusive phenomena in all of science. We'll be diving into the latest theories, the unexpected discoveries, and the brilliant minds that are helping us understand the vast unknowns of dark energy. So sit back, relax, and let's explore the strange science behind the force that's shaping the future of our universe. Welcome to the strange and fascinating world of dark energy, the invisible force that is driving the accelerated expansion of the universe. It's something that has puzzled scientists for decades, and continues to be one of the greatest mysteries in modern physics. Imagine, if you will, a force so powerful that it's not only pushing galaxies apart at incredible speeds, but also shaping the very future of our universe. Yet, despite its monumental effects, no one really knows what dark energy is. We can observe its influence, but its true nature remains elusive. It's as though the universe itself is telling us, I have a secret and you'll have to work a bit harder to figure it out. To understand dark energy, we need to step back in time and take a look at how we came to know about it in the first place. The story begins with the groundbreaking work of a few pioneering minds who helped shape the way we view the cosmos today. One of those minds was Alexander Friedmann, a Russian physicist and mathematician, who, in the early 20th century, proposed a model of the universe that was very different from the one we'd previously imagined. Before Friedmann's work, the prevailing belief was that the universe was static, unchanging, and eternal. But Friedmann showed that based on Einstein's theory of general relativity, the universe could actually be expanding. This was a radical idea, and at the time it didn't gain much attention. However, it would set the stage for the discoveries to come. Fast forward to the 1920s, when Edwin Hubble, an American astronomer, made a discovery that would forever change our understanding of the universe. While observing distant galaxies, he found that they were all moving away from us, and the farther they were, the faster they seemed to be receding. This phenomenon became known as the Hubble law, and it provided the first solid evidence that the universe was indeed expanding, just as Friedmann had predicted. The notion of an expanding universe suddenly became a central piece of cosmology. But even as Hubble's work confirmed this idea, scientists were still left with a burning question. What was driving this expansion? Enter dark energy, the mysterious force that would eventually be revealed as the key to understanding the universe's acceleration. But before we dive into that, let's pause for a moment. For all the excitement that comes with new discoveries, it's important to understand that dark energy didn't simply appear out of nowhere. It was the result of a series of observations, each one building on the other. In the 1990s, two independent teams of astronomers, led by Saul Perlmutter and Brian Schmidt, observed a peculiar thing while studying distant supernovae. These supernovae, which are exploding stars used to measure distances in space, were dimmer than expected. The data suggested that the universe's expansion wasn't slowing down, as had been assumed. Instead, it was speeding up. And to explain this strange acceleration, the scientists concluded that there must be some unseen force at work, something like dark energy. This discovery was a game-changer, and it earned both Perlmutter and Schmidt, along with Adam Riess, the Nobel Prize in Physics in 2014. Their work showed that the universe's expansion wasn't just happening, it was accelerating, driven by an unknown force that we now call dark energy. But even though we can observe its effects, understanding what dark energy actually is remains one of the most profound mysteries in science. Theories abound, but none can fully explain dark energy's true nature. One of the simplest ideas is that dark energy could be tied to the cosmological constant, a term introduced by Albert Einstein in 1917. Einstein initially added this constant to his equations of general relativity to maintain a static universe, but he later abandoned it when it became clear that the universe was expanding. In hindsight, some scientists now believe that the cosmological constant may actually represent the energy of empty space itself, the energy inherent in the vacuum of the universe. But there's more to the story. Some theorists suggest that dark energy might not be a constant at all, but instead a dynamic field that evolves over time, a concept known as quintessence. This idea introduces a form of energy that can change in density, unlike the cosmological constant, which remains fixed. Think of it as a fluid that could stretch and change as the universe ages. Quintessence could help explain some of the observations that don't quite fit with the cosmological constant model. But even this theory is still far from a complete answer. So why is dark energy so important to understand? Well, the influence of dark energy is not only reshaping our current view of the universe, but also determining its future. The fact that dark energy is causing the universe to accelerate means that the very fate of the cosmos is tied to this mysterious force. As the universe continues to expand faster and faster, galaxies will move further apart and eventually distant galaxies will be beyond our reach. This may lead to a future where the universe becomes increasingly empty and dark, stretching out into a cold, desolate void. It's clear that exploring dark energy isn't just a matter of satisfying our curiosity about a single phenomenon. It's about understanding the nature of space, time, and the fundamental forces that shape everything we know. What is the true force behind dark energy? Is it a simple constant, a dynamic field, or something else entirely? We don't know yet, but by studying dark energy, we are learning more about the very structure of the universe itself. As we move forward, we will look at some of the latest theories, examine the controversial debates, and delve into the minds of the scientists working tirelessly to uncover the secrets of dark energy. So, as we journey through the cosmos together, we'll not only explore the past and present of dark energy, but also the future, and the mysterious role this force will play in shaping the universe for eons to come. At the heart of our modern understanding of the cosmos is a discovery so profound that it changed everything we thought we knew about the universe. In the early 20th century, the idea of an expanding universe was born, and with it came the realization that the cosmos wasn't a static, eternal place, as many had previously believed. Instead, it was dynamic and evolving, stretching and growing over time. This insight would eventually lead to the discovery of dark energy, but let's take a step back and look at the trail of discoveries that brought us here. It all began with the work of astronomers like Vesto Melvin Slipher. While today Slipher might not be a household name, his contributions were crucial in laying the groundwork for our understanding of the universe's expansion. In the early 1900s, Slipher was one of the first to measure the redshift of light from distant galaxies. Redshift occurs when light from an object in space shifts toward the red end of the spectrum, indicating that the object is moving away from us. What Slipher discovered was that many galaxies were not only moving away from us but doing so at incredible speeds. This observation was crucial, as it hinted at the possibility that the universe itself was expanding. Yet despite this intriguing data, the idea of an expanding universe wasn't widely accepted at the time. The prevailing view, influenced by the steady-state theory, was that the universe had always been the same size and would continue in this way indefinitely. But in the midst of these debates, Georges Lemaître, a Belgian priest and physicist, stepped in with a bold idea of his own. Lemaître, working independently, came to the conclusion that the universe had indeed been expanding since its origin, a concept that went against the static universe model. In 1927, he published a paper proposing that the universe had started from a single, infinitely dense point, which he referred to as the primeval atom. This was an early version of what we would later call the Big Bang theory, a theory that would reshape our understanding of the cosmos. Lemaître's work set the stage for a revolutionary shift in cosmology, but the world would need more evidence to fully accept it. Then, in 1929, Edwin Hubble, an American astronomer, made a discovery that forever changed how we view the universe. While working at the Mount Wilson Observatory, Hubble observed a variety of galaxies and noted that their light was redshifted, just as Slipher had found. However, Hubble took things a step further. By measuring the redshift of galaxies and comparing it to their distance from Earth, he discovered a pattern. The farther away a galaxy was, the faster it was receding from us. This observation, now known as Hubble's law, was the first solid evidence that the universe was expanding. It was as if the universe itself was stretching, like the surface of a balloon being inflated, carrying galaxies farther apart from each other as it grew. Hubble's findings brought Lemaitre's theory to life and provided undeniable evidence that the universe was dynamic and evolving. However, this discovery didn't immediately explain everything. While Hubble's law provided a clear picture of an expanding universe, scientists were still left to wonder about the force behind this expansion. What was driving it? Why did the galaxies continue to recede from each other? One possible answer lay in Albert Einstein's cosmological constant. Originally, Einstein had introduced the cosmological constant in his equations of general relativity in 1917. At the time, Einstein was trying to create a model of the universe that was static, unchanging and eternal, a view that matched the conventional wisdom of the day. However, as we now know, the universe is anything but static. Einstein later referred to his cosmological constant as his biggest blunder when he abandoned it, after realizing that the universe was expanding. Despite this, the idea of the cosmological constant didn't disappear. In fact, it has made a dramatic comeback in modern cosmology, as it's now thought that this constant could be a key to understanding dark energy. But before we get too deep into that, let's take a moment to reflect on what these early discoveries accomplished. Thanks to the work of Slipher, Lemaitre, Hubble and Einstein, we were starting to realize that the universe wasn't the fixed, immutable place that many had once believed. It was evolving, stretching out into the vastness of space. This was a game changer in itself, but there was still so much more to uncover. Now we enter the world of supernovae. These brilliant explosions of dying stars would become one of the most important tools for cosmologists in the search for dark energy. In the 1990s, two separate teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt, began observing distant supernovae. These exploding stars are incredibly bright and can be used as standard candles or objects whose intrinsic brightness is well understood. By measuring how bright a supernova appears from Earth, astronomers can determine how far away it is. And so, when these teams began studying supernovae, they expected to find that the universe's expansion was slowing down, as the gravitational pull of galaxies should eventually cause the expansion to decelerate. Instead, they found the opposite. The distant supernovae were dimmer than expected, indicating that they were farther away than they should be if the expansion was slowing. In other words, the universe wasn't slowing down at all, it was speeding up. This unexpected result forced scientists to consider the possibility of some unseen force driving the acceleration of the universe. That force, as we now understand, is dark energy. The discovery of the accelerating universe was revolutionary, and it opened the door for scientists to explore this mysterious force and its implications for the future of the cosmos. The findings of Perlmutter, Schmidt, and their teams earned them the Nobel Prize in Physics in 2014, solidifying their contributions to the field of cosmology. As we venture deeper into the mysteries of dark energy, it's important to remember that these discoveries didn't come from a single breakthrough moment. Instead, they were the result of decades of work, observation, and the contributions of brilliant scientists, each building upon the work of those who came before them. From Slipher's redshift measurements to Lemaitre's primeval atom and Hubble's cosmic law, every step brought us closer to understanding the universe's true nature. Now, as we look at supernova and the evidence they provide for the universe's accelerating expansion, we are reminded of how much we still don't know about the forces at play. Dark energy, the invisible force behind this acceleration, is one of the greatest unsolved mysteries in modern science. And as we continue to explore its effects on the universe, we can only wonder, what other secrets does the cosmos hold waiting to be uncovered? As we continue our journey through the cosmos, it's time to focus on one of the most powerful tools in the astronomer's toolbox, supernovae. These explosive deaths of massive stars have provided us with some of the most valuable insights into the universe, particularly its expansion. For decades, astronomers have used supernovae to measure distances across the universe, but it wasn't until the 1990s that they became central to uncovering one of the most significant discoveries in modern cosmology: the acceleration of the universe's expansion. Supernovae, particularly Type 1a supernovae, have a unique feature that makes them ideal for measuring cosmic distances. These stars explode with a remarkable consistency in terms of brightness, which allows scientists to use them as what we call standard candles. In other words, by studying the light emitted by a Type 1a supernova, astronomers can determine its intrinsic brightness, and by comparing that to how bright it appears from Earth, they can figure out how far away the supernova is. In the 1990s, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt, were using these supernovae to measure the rate of expansion of the universe. They expected to find that the universe was slowing down over time, a consequence of gravity pulling galaxies toward each other. Instead, they were stunned to discover that the distant supernovae were dimmer than they should have been, indicating that they were farther away than expected. This surprising result suggested that the universe wasn't slowing down at all. In fact, it was expanding faster than ever, and something unknown was driving this acceleration. That unknown force, of course, would eventually be identified as dark energy. This groundbreaking discovery led to the recognition that dark energy, a mysterious force that we still don't fully understand, is the driving force behind the accelerated expansion of the universe. It was a profound shift in how we think about the cosmos, but the story doesn't stop there. In fact, supernovae have also led to some surprising new avenues of research, showing that the universe's expansion might not be as straightforward as we once thought. One scientist whose work has helped shed light on these questions is David Tytler, a researcher who has focused on the abundances of elements in the universe. His work provides key insights into the early universe, specifically how elements like hydrogen, helium, and lithium were created during the Big Bang. Tytler's findings suggest that the way these elements are distributed throughout the cosmos might be linked to the nature of dark energy itself. If dark energy is truly responsible for the acceleration of the universe, then its effects could be written into the very fabric of the universe's composition. By studying the abundance of elements in distant galaxies, Tytler's research hints that dark energy might be a much more integrated part of the cosmos than we initially imagined. While the discovery of the accelerating universe is exciting, it also raises some fundamental questions that challenge our current understanding of physics. For example, Nima Arkani-Hamed, a leading physicist, has proposed theories that suggest quantum gravity could play a key role in explaining the behavior of supernovae and dark energy. Quantum gravity is the study of how quantum mechanics and general relativity, two of the most successful theories in physics, can be reconciled into a single unified framework. Arkani-Hamed's research suggests that supernovae measurements, which are used to measure the rate of expansion, might actually reveal more about the nature of gravity at cosmological scales than we realize. He proposes that quantum gravitational effects could influence the behavior of supernovae and their light, potentially causing some of the strange results we observe. This would mean that the acceleration of the universe could be explained by a more fundamental aspect of nature, rather than dark energy alone. Now, with all of this in mind, it's important to consider the possibility that our interpretation of supernova data might not be entirely correct. After all, supernovae are incredibly complex events, and there are still many variables that scientists don't fully understand. Could it be that the surprising results we're seeing are not actually caused by dark energy, but by something else entirely? Some scientists, like Milton J. Rosenblum, have suggested that the apparent acceleration of the universe might be the result of something more subtle: cosmic fluctuations. According to Rosenblum's theory, the universe could be experiencing a kind of cosmic noise, a background hum of fluctuations in the fabric of space-time itself. These fluctuations might be influencing our measurements of distant supernovae, leading us to mistakenly conclude that the universe is accelerating when in fact it's simply responding to these unpredictable cosmic effects. This idea, if true, would be a fascinating challenge to our current understanding of the universe's expansion. Instead of dark energy, which is an inherently mysterious and somewhat unsettling force, we might be dealing with something more familiar: the inherent unpredictability of the cosmos. If cosmic fluctuations are responsible for the apparent acceleration, then the universe might be behaving in ways we haven't fully accounted for yet. As we consider these alternative theories, it's important to remember that dark energy is still the leading explanation for the acceleration of the universe. But the fact that supernovae can also point us in the direction of quantum gravity or cosmic fluctuations shows just how much we still don't know. Our understanding of the universe is constantly evolving, and every new discovery brings us one step closer to understanding the forces that shape our reality. Whether it's dark energy, quantum effects, or something entirely unexpected, one thing is certain. The cosmos has much more to reveal, and the role of supernovae in this journey is far from over. As we continue to probe the mysteries of the universe, we'll be looking at more theories that challenge the standard models and dig deeper into the nature of dark energy. The road ahead is filled with intriguing possibilities, and the next step in our journey will be to explore how the very fabric of space-time might be influenced by dark energy in ways we haven't yet imagined. With supernovae as our guide, we'll venture further into the unknown, uncovering new truths about the universe with each discovery. When it comes to dark energy, there's no shortage of theories, each attempting to explain the mysterious force that is driving the accelerated expansion of the universe. The most widely accepted model, and the one that has stood the test of time, is the cosmological constant. Introduced by Albert Einstein in 1917 as part of his theory of general relativity, the cosmological constant originally served as a fudge factor to keep the universe static. At the time, Einstein believed the universe was unchanging, and this constant allowed his equations to describe such a model. However, when it was later discovered that the universe was not static but expanding, Einstein discarded the constant, famously calling it his biggest blunder. Despite this, the cosmological constant made a dramatic comeback in the 1990s, when scientists studying distant supernovae discovered that the universe's expansion was not slowing down, as they had expected, but accelerating. In response to this unexpected finding, dark energy was proposed as the culprit, and the cosmological constant was resurrected as a possible explanation. In this modern context, the cosmological constant represents a form of energy that is inherent in empty space itself, a sort of vacuum energy that acts like a force of repulsion, causing the universe to expand at an ever-increasing rate. While the cosmological constant is the simplest model, it's not the only one. In fact, some scientists argue that it's too simple, and that we need a more dynamic and flexible model to fully explain dark energy. Enter quintessence, a more complex theory that proposes dark energy is not a constant force, but one that evolves over time. Unlike the cosmological constant, which remains the same throughout the life of the universe, quintessence suggests that the energy density of dark energy could change as the universe ages. This model introduces the idea of a dynamic scalar field that influences the expansion of the universe in a more variable way, and it could potentially explain some of the observations that the cosmological constant model cannot fully account for. The idea of quintessence provides a fascinating twist on the concept of dark energy, but the theories don't stop there. One scientist whose work offers a radically different perspective is Eric J. Weinberg, a prominent physicist known for his contributions to string theory. String theory, which aims to unify the forces of nature by describing particles as tiny, vibrating strings, suggests that the fundamental nature of reality is much more complex than we can currently understand. Weinberg's work on dark energy is built on the idea that our universe may exist within a higher dimensional space, and that the effects of dark energy might be a consequence of the geometry of these extra dimensions. In this multidimensional view of the universe, dark energy could be a result of the way these higher dimensions interact with our observable universe, pushing galaxies apart in ways that we are only beginning to understand. Weinberg's approach connects dark energy with the deepest aspects of theoretical physics, tying it to the broader quest for a unified theory of everything. Building on this idea of cosmic complexity, Lee Smolin offers another intriguing perspective with his theory of cosmological natural selection. In Smolin's view, dark energy might not just be a force in our universe, but a feature of the universe itself that arises through a process of natural selection. He proposes that the laws of physics, including the properties of dark energy, could evolve over time with each new universe born from the collapse of an older one, inheriting and modifying the physical laws of its predecessor. This process, which Smolin calls cosmological natural selection, might explain why our universe has the particular properties it does, including the value of dark energy that drives the accelerated expansion. According to Smolin, dark energy could be a product of this process, and understanding it might reveal deeper truths about the nature of existence and the multiverse. Another theory that adds a new layer to our understanding of dark energy comes from Axel Brandenburg, a researcher who has proposed that the mysterious force might be linked to cosmic dynamos, the same processes that power the magnetic fields of stars and galaxies. Brandenburg's work suggests that dark energy could be connected to the electromagnetic forces at play in the universe, specifically the way cosmic fluids move and generate magnetic fields. He proposes that the behavior of these fluids on a cosmic scale could be influencing the expansion of the universe in ways we hadn't considered. This theory is still in its early stages, but it offers a novel way to connect dark energy with the broader forces of electromagnetism and magnetism in space. While these theories offer fascinating possibilities, they also challenge some of the assumptions we've made about dark energy. For instance, Marcelo Gleiser, a physicist and cosmologist, has taken a different approach with his idea of chaotic cosmology. Rather than assuming that the universe follows a neat, orderly set of physical laws, Gleiser's theory suggests that the cosmos is inherently chaotic and unpredictable. In his view, dark energy could be a product of this chaos, a manifestation of the random fluctuations and emergent behaviors that arise in a universe that is constantly changing. According to Gleiser, the accelerating expansion of the universe may not be driven by a fixed force like the cosmological constant or a dynamic field like quintessence, but by the intrinsic unpredictability of the universe itself. If Gleiser's chaotic cosmology is correct, then dark energy might not be a single, coherent force, but a collection of effects that arise from the complex, evolving nature of the universe. As we explore these theories, it becomes clear that the nature of dark energy is still very much an open question. While the cosmological constant and quintessence remain the leading contenders, more radical ideas like those of Weinberg, Smolin, Brandenburg, and Gleiser are pushing the boundaries of our understanding, forcing us to reconsider the fundamental forces at work in the universe. Each of these theories brings something valuable to the table, whether it's the idea of extra dimensions, the evolution of physical laws, or the connection between electromagnetism and cosmic expansion. As we continue to grapple with the mystery of dark energy, we must remain open to new ideas and be willing to challenge our current models. The universe is vast and full of surprises, and the answers to its deepest mysteries might lie in theories that are still in their infancy. In the next chapter, we'll explore the debates and controversies surrounding dark energy, as well as the scientific community's efforts to test these theories and find a clearer path toward understanding the true nature of the force that's driving the expansion of the universe. The search for answers is ongoing, and with each new discovery we come closer to unlocking the secrets of the cosmos. As our understanding of dark energy deepens, so too does the level of debate surrounding it. The discovery that the universe is accelerating in its expansion has left scientists scrambling to find a satisfactory explanation. And while dark energy has become the leading theory, it's far from universally accepted. This ongoing controversy is a natural part of scientific progress, but it highlights just how much remains unknown about the true nature of the cosmos. One of the most vocal critics of the cosmological constant, the model that has been widely used to explain dark energy, is Sabine Hossenfelder, a theoretical physicist known for her critique of various mainstream theories. Hossenfelder argues that the cosmological constant, though useful in fitting the data we currently have, is fundamentally flawed. She points out that it introduces a huge discrepancy between the value predicted by quantum field theory and the much smaller value observed in cosmology. This difference, often referred to as the cosmological constant problem, is one of the major unsolved issues in physics. Hossenfelder suggests that perhaps the cosmological constant isn't the right answer at all, and that we need to look for new models that better explain the observed acceleration of the universe. Hossenfelder's skepticism has led to alternative interpretations of dark energy that could explain cosmic acceleration without relying on the cosmological constant. One such alternative is the idea that gravity itself might be behaving differently on cosmological scales. This leads us to the work of James Peebles, one of the leading cosmologists of the last few decades. Peebles has proposed that the acceleration of the universe might be explained by modifications to Einstein's theory of general relativity. In his view, dark energy might not be a separate force, but instead a result of the way gravity operates over vast distances. Peebles suggests that the traditional models of gravity, which work well in local systems, might need to be adjusted when applied to the universe as a whole. Modifying gravity on large scales could potentially account for the accelerated expansion without requiring an unknown force like dark energy. This idea of modifying gravity is not entirely new. In fact, various theories have been proposed over the years that suggest our understanding of gravity might need refinement. One such theory is modified Newtonian dynamics, MOND, which proposes that gravity behaves differently at very large distances. Peebles' approach takes this idea even further, suggesting that there could be a form of gravity that changes over time and space, leading to the observed cosmic acceleration. While his theories are still speculative, they raise important questions about the assumptions we've made about gravity and whether we need to rethink some of the fundamental laws of physics. But even as we debate whether dark energy is real or just an artifact of our measurements, there's another, more provocative question that emerges. Could dark energy be the result of errors in our observations? This idea challenges the very foundations of our cosmological models, and it's something that Ariadne N. F. P. Finkel, an astrophysicist who's worked extensively on cosmic distances and the calibration of observational methods, has suggested. Finkel's research questions whether we've been misinterpreting the data that suggests an accelerating universe. Could the distance measurements to distant supernovae be flawed? Could the assumptions we've made about the uniformity of the universe be incorrect? Finkel's work advocates for a more cautious approach, urging scientists to revisit the data and the methods we've used to interpret it. If her hypothesis is correct, it would mean that dark energy might not be the cause of the accelerated expansion at all. Instead, it could be the result of a systematic error in how we measure distances across the universe. This perspective introduces a fascinating wrinkle to the dark energy debate. If dark energy is not the cause of cosmic acceleration, then what is? Are we truly on the right track, or is the answer still hiding in plain sight, just waiting for us to take a step back and reassess our observations? Finkel's challenge to the conventional interpretation of dark energy forces us to reconsider how we gather and analyze cosmological data, and it pushes the boundaries of what we know about the universe. Despite these challenges and controversies, dark energy remains the leading explanation for the acceleration of the universe. However, the debates are far from settled. As more and more theories emerge, each with its own strengths and weaknesses, it becomes clear that our understanding of dark energy is still evolving. The question of whether dark energy is a real force, or a result of observational errors, will require further investigation, and the ongoing debates will undoubtedly shape the future of cosmology. This uncertainty has led to a flurry of new experiments and observational techniques aimed at resolving these questions. Telescopes and observatories like the Dark Energy Survey (DESIS), the Euclid mission by the European Space Agency, and the Wide Field Infrared Survey Telescope WFIRST by NASA are all designed to gather more precise data about the universe's expansion and the role of dark energy. These experiments will provide more accurate measurements of supernovae, galaxy clusters, and the cosmic microwave background, key indicators that will help us refine our models and test the theories we've discussed. By measuring the distribution of galaxies and their motions with greater precision, these upcoming experiments could give us new insights into whether dark energy is a true force, a modification of gravity, or something else entirely. As we continue to explore these questions, we're reminded of the complexity of the universe. Dark energy, whether it's a real force or a result of observational error, challenges our understanding of the cosmos in profound ways. The controversies surrounding dark energy reflect the excitement of scientific discovery. Each theory and counter-theory brings us one step closer to understanding the true nature of the universe. The debates are far from over, and as new data pours in, the answers will gradually emerge. In the next chapter, we'll take a closer look at some of the experiments that are being designed to settle these debates once and for all. With each new discovery, we get one step closer to unlocking the mysteries of dark energy and, perhaps, discovering the underlying truths about the universe itself. As the quest to understand dark energy continues, astronomers and physicists around the world are relying on some of the most cutting-edge experiments and missions ever devised to gather new data. These missions promise to provide the most accurate and detailed measurements yet, offering the potential to refine or even challenge our current models of dark energy. The future of dark energy research lies in the observations and discoveries that these upcoming experiments will bring. One of the most ambitious projects currently underway is the Euclid mission by the European Space Agency. Set to launch in the coming years, Euclid's primary goal is to map the geometry of the dark universe with unprecedented precision. It will do this by observing the large-scale structure of the universe, galaxies, clusters, and superclusters, and measuring how they have been stretched by the expansion of space-time. Euclid will focus particularly on the way dark energy affects the expansion of the universe, as it will provide highly accurate measurements of the cosmic acceleration that's believed to be caused by dark energy. The mission is equipped with a powerful camera and spectrometer, allowing it to capture vast areas of the sky in remarkable detail. By studying the distribution and movement of galaxies across cosmic time, Euclid will provide key insights into the behavior of dark energy and how it might be evolving over time. Alongside Euclid, the Wide Field Infrared Survey Telescope, or WFIRST, is another mission that promises to deepen our understanding of dark energy. This telescope, funded by NASA, is set to study the expansion of the universe through a technique known as weak gravitational lensing. This method involves measuring the subtle distortions in the light of distant galaxies caused by the gravitational pull of foreground objects. By mapping these distortions across the sky, WFIRST will provide a detailed picture of the cosmic web and how it has evolved under the influence of dark energy. The data collected by WFIRST will be crucial for testing current theories of dark energy and could reveal new information about its properties. Much like Euclid, WFIRST will also provide valuable data on galaxy clusters, supernovae, and the cosmic microwave background, helping to piece together the puzzle of the universe's accelerating expansion. Meanwhile, the Dark Energy Spectroscopic Instrument, DESI, currently in operation, is a groundbreaking experiment designed to map the three-dimensional distribution of galaxies across the universe. By measuring the redshift of more than 30 million galaxies, DESI aims to create a detailed map of the universe's expansion. One of its key goals is to better understand the role of dark energy in the cosmos by analysing how galaxies have been stretched over time. By combining this data with information from other telescopes and missions, DESI will help refine the current models of dark energy, allowing scientists to test whether it behaves as a constant force or if it changes over time. This large-scale survey will provide a wealth of data that will be critical for understanding the fundamental forces shaping the universe. But it's not just telescopes and galaxy surveys that are shedding light on dark energy. Gravitational waves, ripples in space-time caused by massive objects like merging black holes, are also playing an important role in dark energy research. The study of gravitational waves has already opened a new window into the cosmos, and researchers like Kip Thorne, a leading theorist in gravitational physics, have explored how these waves could help us understand the nature of dark energy. Gravitational waves are a direct probe of space-time, and by studying their interactions with distant galaxies and cosmic structures, scientists hope to uncover more about how dark energy affects the fabric of space-time itself. One exciting possibility is that gravitational waves might provide clues about the cosmic acceleration. If dark energy is influencing the expansion of the universe, it could also have an effect on the way space-time responds to gravitational waves. By comparing the speed and behavior of these waves across different regions of the universe, scientists might be able to detect subtle differences caused by dark energy's influence. The combination of gravitational wave astronomy and traditional methods like galaxy surveys could offer a more comprehensive view of the cosmos than ever before, revealing new insights into the nature of dark energy and its role in shaping the universe. The data from these missions and experiments will not only help us refine our current models of dark energy, but may also challenge some of our existing assumptions. For example, as we continue to gather more data, we may find that dark energy is not a single force at all, but a collection of phenomena that emerge from the interplay of different forces, such as gravity, quantum fluctuations, and even the mysterious nature of space-time itself. It's also possible that the current theories, such as the cosmological constant or quintessence, may need to be adjusted, or that completely new models will emerge, offering a fresh perspective on the universe's accelerating expansion. But the road ahead is filled with unknowns. As we gather more data, we are likely to encounter new surprises, some of which may not fit into the neat boxes of our current models. The complexity of dark energy means that each new discovery could lead to even more questions. But this is the nature of scientific inquiry. Every answer opens the door to new mysteries. While we are far from fully understanding dark energy, the upcoming missions and experiments will bring us closer to the truth. The discoveries we make in the next few decades could redefine our understanding of the universe and our place within it. As we move forward, we will continue to explore these new frontiers of cosmic exploration, uncovering more about dark energy and the forces that govern the vast expanse of space. The results from these missions will help us better understand the fate of the universe itself and how dark energy will shape its ultimate destiny. The exciting journey into the heart of the universe's most elusive force is only just beginning, and each new piece of data brings us one step closer to unraveling the mysteries of dark energy. As we look out into the far reaches of the universe, one of the most profound questions we can ask is, what will happen to it in the distant future? The discovery of dark energy has raised the stakes, forcing us to reconsider the long-term fate of the cosmos. No longer can we simply think of the universe as a static, unchanging entity. With dark energy driving the accelerating expansion of space, the future of the universe is inextricably linked to this mysterious force. What we now understand is that the universe is not only expanding, but it is speeding up, stretching farther apart with each passing moment. One possible scenario for the universe's ultimate fate is what Frank J. Tipler calls the omega point. Tipler's theory is based on the idea that as the universe evolves, it will eventually reach a state of maximum complexity and intelligence, a point where all life and consciousness will be able to experience the entire history of the universe in a single moment. According to Tipler, this omega point will be the culmination of cosmic evolution, driven by the power of dark energy and the continued expansion of the universe. As the universe approaches this final state, everything will become more tightly compressed, and time itself may become infinite, allowing for a perfect, eternal understanding of the cosmos. The theory suggests that dark energy plays a crucial role in accelerating the universe to this point, as it is responsible for the continuous expansion that drives the universe toward its ultimate, inevitable conclusion. However, not all theories agree on such a peaceful and harmonious end. Ervin Laszlo, a systems theorist and philosopher of science, proposes a very different view of the universe's end, known as the Akashic Field. Laszlo's theory suggests that the universe is not a random chaotic place, but rather a deeply interconnected system, where all matter and energy are linked through a field of information. In this view, dark energy could be a manifestation of the underlying order of the cosmos, serving as a catalyst for the universe's evolution. When the universe eventually reaches its end, which Laszlo believes is not an ending at all, it will enter a state of ultimate unity, where all the information and energy of the cosmos will converge into a single, unified field. This field, which he refers to as the Akashic Field, is a repository of all knowledge and experience. In this final state, the universe's expansion will have reached its ultimate potential, driven by the effects of dark energy, and will give way to a new phase of existence that transcends the physical limitations of space and time. These theories, though vastly different, share a common thread. They both propose a future shaped by the expanding universe and the influence of dark energy. But there's another scenario, one that has gained increasing attention in cosmological circles, and it's much less serene. This scenario is known as the Big Rip, and it presents a much more dramatic end to the universe. The Big Rip scenario is based on the idea that as dark energy continues to drive the universe's expansion, it will eventually reach a point where it overpowers all other forces in the universe. The force of dark energy would then begin to stretch not just galaxies and stars apart, but even the very atoms and subatomic particles that make up all matter. In the Big Rip, everything, planets, stars, galaxies, and even the fabric of space-time itself, would be torn apart. The timeline for such a catastrophic event depends on the precise nature of dark energy, and whether it remains constant or evolves over time. If dark energy's strength increases as the universe expands, as some models suggest, the Big Rip could occur in about 20 billion years or so. It's a dramatic and somewhat terrifying scenario that paints a picture of a universe in which the accelerating expansion eventually leads to complete disintegration. What makes the Big Rip scenario particularly interesting is its connection to dark energy's fundamental properties. If dark energy behaves like a cosmological constant, the universe's expansion will continue to accelerate indefinitely. But the scenario of the Big Rip becomes more likely if dark energy becomes stronger over time. This would mean that the repulsive force driving the expansion of the universe would eventually overwhelm gravity, pulling apart galaxies, stars, and everything else, until even atoms themselves would be torn apart by the relentless stretch of space. The fate of the universe would then be sealed, with a violent end that arises directly from the influence of dark energy. While the Big Rip is certainly an unsettling idea, it also raises important questions about the true nature of dark energy. Is it truly a constant, or is it evolving in a way that will lead to such a dramatic conclusion? What role does dark energy play in the long-term dynamics of the universe? These are questions that we are still struggling to answer, but the implications of these theories are enormous. Whether we are headed for a peaceful omega point, a unified Akashic field, or the violent Big Rip, one thing is certain: dark energy will be a key player in determining the future of the universe. As we continue to explore the mysteries of dark energy, it's important to remember that these are not just abstract theories. The fate of the universe is tied to the very nature of the force that we're still working to understand. Every new observation, every new experiment, and every new theory brings us closer to answering some of the most profound questions about the cosmos. In the next chapter, we'll begin to explore how dark energy might relate to the strange and mysterious world of quantum mechanics. We'll dive into the potential connections between dark energy and the quantum forces that govern the behavior of particles at the smallest scales. As we move forward, we'll continue our journey into the unknown, with dark energy as our guide, pushing the boundaries of what we know and revealing the true nature of the universe. At the heart of modern physics lies a strange and mysterious relationship between dark energy and quantum mechanics. The two concepts, dark energy, a force driving the accelerated expansion of the universe, and quantum mechanics, the science of the smallest particles and their behaviors, might seem like they belong to entirely different realms. But as we delve deeper into the mysteries of the cosmos, we begin to see that the two may be intricately linked, with dark energy offering us a unique window into understanding the true nature of space-time itself. Let's begin by looking at one of the most fascinating features of quantum mechanics: quantum vacuum fluctuations. In the quantum world, empty space is never truly empty. Instead, it's filled with fleeting temporary fluctuations in energy. These fluctuations are a direct consequence of the uncertainty principle, a fundamental concept in quantum mechanics that tells us we cannot know certain pairs of properties, such as position and momentum, with absolute precision. Because of this uncertainty, particles and energy seem to pop in and out of existence in the vacuum of space. These fluctuations are incredibly small, but they have a profound impact on the nature of the universe. Quantum vacuum fluctuations have a direct connection to dark energy, as they suggest that even in a vacuum, energy is constantly being generated. It's this background energy, arising from quantum fields, that may be closely related to the dark energy that drives the expansion of the universe. Essentially, what we observe as dark energy might be the large-scale manifestation of these tiny, quantum fluctuations on a cosmic scale. This idea has profound implications because it suggests that the vacuum itself, the space between particles, is a dynamic, energy-filled environment that influences the very fabric of the universe. Two of the leading scientists who have explored the connection between quantum mechanics and dark energy are Steven Weinberg and Roger Penrose, both of whom have spent much of their careers seeking to bridge the gap between the micro and macro worlds of physics. Weinberg's work on quantum field theory has shown that the energy of quantum fluctuations can be linked to the cosmological constant, a model often used to describe dark energy. In Weinberg's view, the vacuum energy generated by these fluctuations is responsible for the accelerated expansion of the universe. His theories suggest that understanding how the vacuum behaves on both the quantum and cosmic scales could provide crucial insights into dark energy's role in the universe. On the other hand, Roger Penrose, famous for his contributions to black hole theory and general relativity, has taken a slightly different approach. Penrose has long been interested in the nature of space-time itself, and he has suggested that the quantum vacuum might be more than just a source of energy. In his view, the quantum vacuum could play a deeper role in the evolution of the universe, influencing the very structure of space and time. Penrose proposes that quantum processes may not just affect the universe locally, but could be responsible for larger cosmic events, such as the acceleration of the universe driven by dark energy. His work suggests that dark energy might be tied to the very fabric of space-time, and that understanding its quantum properties could reveal much more about the true nature of the cosmos. Building on these ideas, Marcel von Lane has proposed an interesting perspective, that dark energy might actually emerge directly from quantum field fluctuations. According to von Lane, dark energy is not just a product of the vacuum energy, but a direct result of the interaction between quantum fields. In his model, the fluctuations of quantum fields in the vacuum give rise to the effects of dark energy, pushing space apart and accelerating the universe's expansion. This idea challenges the conventional view of dark energy as a simple, uniform force. Instead, Von Lane's work suggests that dark energy is the product of a much more complex and dynamic interaction at the smaller scales of the universe. In addition to these ideas, Carlo Rovelli and Abhay Mehta, both prominent researchers in the field of quantum gravity, have explored how dark energy might be tied to the unification of quantum mechanics and general relativity. The theory of quantum gravity seeks to explain how the gravitational force, which governs the behavior of massive objects like stars and galaxies, works at the quantum level, while general relativity describes the large-scale structure of space-time with remarkable precision. Quantum mechanics rules the behavior of subatomic particles. However, the two theories have never been successfully combined, leaving us with an incomplete picture of the universe. Rovelli and Mehta have suggested that dark energy might provide a key insight into this unification. According to their theories, dark energy could be a manifestation of quantum gravitational effects that we have yet to fully understand. These effects could influence the expansion of the universe by altering the geometry of space-time itself. If dark energy is related to quantum gravity, then it could be a direct consequence of the way space-time behaves on the smallest scales. This idea opens up exciting possibilities for understanding not only dark energy, but also the true nature of space-time itself. At the heart of all these theories lies the idea that dark energy is intimately connected to the structure of space and time, as well as the underlying quantum fields that fill the universe. This connection has the potential to reveal much more than just the origins of dark energy. By understanding how dark energy interacts with quantum mechanics and the fabric of space-time, we might be able to uncover the deeper laws of nature that govern the universe. In a way, dark energy acts as a bridge, linking the vast cosmic scales of the universe with the tiny quantum world of particles and fields. But as we venture deeper into the mysteries of dark energy, we also find that it offers us a glimpse into the very heart of reality itself. If dark energy is tied to quantum fluctuations and quantum gravity, it could help us answer some of the most profound questions in physics. How does space-time behave on the smaller scales? What is the true nature of the quantum vacuum? And what are the fundamental forces that shape our universe? By studying dark energy, we may be able to uncover the answers to these questions, revealing a deeper understanding of the universe's structure and its ultimate fate. As we continue to explore the fascinating connection between dark energy and quantum mechanics, we'll also start to see how this force interacts with the fabric of space-time itself. Dark energy, with its mysterious properties, might hold the key to understanding the true nature of space and time. And as we begin to unlock these secrets, we may find that the answers we seek are closer than we ever imagined. The journey into the heart of dark energy is just beginning, and with each new discovery we move one step closer to understanding the fundamental workings of the universe. Dark energy is an enigma that has fascinated scientists for decades, but beyond its role in accelerating the expansion of the universe, it holds an even more profound mystery. How might it be altering the very fabric of space-time itself? This idea challenges our understanding of space as a static, unchanging backdrop, and suggests that the universe is not just expanding in space, but also reshaping the space in which it exists. In a way, dark energy might be rewriting the laws that govern the cosmos, and in doing so, transforming our view of the universe's evolution. One of the great minds who contributed to our understanding of space-time was John Archibald Wheeler, a physicist whose work in the mid-20th century helped shape modern ideas about the universe. Wheeler famously described space-time as a fabric that could be warped and distorted by mass and energy. He saw this fabric not as a passive stage for cosmic events, but as an active participant in the evolution of the universe. According to Wheeler, space-time is not just a stage where things happen, it is a dynamic, evolving entity that responds to the forces within it. Wheeler's ideas on space-time have profound implications when we consider dark energy. If space-time is truly a flexible fabric, then dark energy could be the force that stretches it, pulling the universe apart at an accelerating rate. Dark energy may not just be an invisible force acting upon the universe from the outside, it could be intrinsically connected to the geometry of space-time itself. This view aligns with the general theory of relativity, developed by Albert Einstein in the early 20th century, which shows how mass and energy curve the fabric of space-time. In this framework, space-time is not a fixed stage but a flexible entity that responds to the energy within it. The concept of space-time curvature is central to our understanding of gravity. When we think about the role dark energy plays, we might imagine it as something that causes space-time to stretch and expand, much like a balloon being inflated. This stretching isn't just the result of matter and energy being distributed throughout space. Instead, dark energy could be contributing directly to the very expansion of space itself. The more space expands, the more dark energy appears to be at work, pushing the fabric of space-time further apart. In this context, the universe's accelerating expansion takes on a new dimension. The expansion of space-time isn't just a matter of galaxies moving away from each other. It's a fundamental reshaping of the very geometry of the cosmos. The more we learn about dark energy, the more we realize that its influence could be deeply intertwined with the structure of space-time. As the universe expands, dark energy might be pushing against the very geometry of space-time, altering how we think about distance, time, and the connections between galaxies. This relationship between dark energy and space-time geometry leads us to a deeper understanding of the universe's stretching. The idea of space-time stretching is not a new one. It's an inherent part of the expanding universe model. But the role of dark energy adds a new layer of complexity. In the traditional view of the expanding universe, galaxies move apart because space itself is stretching. But the rate of expansion was expected to slow over time due to the gravitational pull of matter. Instead, dark energy has been observed to accelerate the expansion, causing galaxies to move farther apart faster than we ever expected. This effect seems to be related to the way space-time itself is stretching, and dark energy could be the force that drives this accelerated expansion. The link between dark energy and space-time also raises questions about how the fabric of space-time behaves on a universal scale. As dark energy pushes the universe apart, it might be altering the properties of space-time itself, perhaps even changing the way we understand fundamental forces like gravity. This could have profound implications for our understanding of the universe's ultimate fate. If dark energy continues to accelerate the expansion, it may eventually lead to a scenario where galaxies and other cosmic structures become so far apart that the universe becomes increasingly isolated, with stars and galaxies beyond our observational reach. This scenario, sometimes referred to as the Big Freeze, is just one possible outcome of dark energy's influence on space-time. As we look toward the future of dark energy research, it's clear that understanding its role in the fabric of space-time is crucial. Dark energy may not only be responsible for the expansion of the universe, but it could also hold the key to unlocking the true nature of space and time itself. Scientists are already exploring new ideas about how dark energy could be manipulated or understood in the context of quantum mechanics, with the goal of understanding how these fundamental forces interact on the smallest and largest scales. By studying how dark energy influences the geometry of space-time, we might be able to gain new insights into the fundamental structure of the universe. One exciting area of research is the potential for space-time manipulation. The idea that understanding dark energy's effects on space-time could lead to new ways of controlling or manipulating the fabric of the cosmos. While this may sound like science fiction, it's rooted in the idea that space-time itself is dynamic and responsive to forces like dark energy. If we can understand the mechanics of dark energy and how it interacts with space-time, we may one day be able to manipulate these forces in ways that could have far-reaching consequences for the future of science and technology. The future of dark energy research is undoubtedly one of the most exciting frontiers in physics. As we continue to study its effects on space-time, we are likely to encounter new and surprising revelations that challenge our current understanding of the universe. Dark energy is not just a force that drives the expansion of the universe. It is a key to understanding the deepest mysteries of space and time, and it may hold the answers to questions we have yet to even ask. As we move forward in our exploration of dark energy, we will uncover new connections between the quantum world, gravity, and the very structure of space itself. The journey into the heart of dark energy is far from over, and with each new discovery we move closer to understanding the true nature of the cosmos and the forces that shape it. Dark energy and dark matter are two of the most intriguing and mysterious components of the universe, yet they are often mentioned in the same breath as if they are one and the same. However, these two phenomena are not only vastly different from one another, but also play distinctly separate roles in the cosmic dance of the universe. Understanding how dark energy and dark matter differ from each other is crucial to understanding how they influence the universe's evolution and structure. Let's start with the basics. Dark energy is the force believed to be responsible for the accelerated expansion of the universe. It works in opposition to gravity, driving galaxies further apart over time. In contrast, dark matter is a mysterious form of matter that doesn't emit, absorb, or reflect light, making it invisible to traditional observational methods. However, its presence can be inferred through its gravitational effects on visible matter, such as stars and galaxies. Unlike dark energy, which pushes galaxies apart, dark matter pulls matter together, acting as the glue that holds galaxies and galaxy clusters together. Both are invisible, but they exert their influence in very different ways. One of the scientists who has significantly contributed to understanding the relationship between dark energy and dark matter is Subir Sarkar, a theoretical physicist known for his work on cosmology and the cosmological tensions in our understanding of the universe. Sarkar has pointed out that the differences between dark energy and dark matter could be more profound than previously thought. He suggests that these two phenomena may not only influence cosmic dynamics in different ways, but they might even be part of a broader unified picture that we have yet to fully grasp. Sarkar's work highlights the tensions within the current models of cosmology, particularly when it comes to reconciling the effects of dark matter and dark energy. While dark matter helps in the formation of galaxies and structures within the universe, dark energy drives the universe's expansion, pushing these structures farther apart. These opposing influences are a reminder that there's still much we don't know about the underlying forces of the universe. Some theories, like those proposed by George Ellis, suggest that dark energy and dark matter could in fact be related through a unified field theory. In Ellis's view, both dark energy and dark matter could be manifestations of a deeper, underlying force that governs the cosmos. A unified field theory aims to describe all fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces as parts of a single, cohesive framework. By extending this idea to dark energy and dark matter, Ellis proposes that both may be different aspects of the same cosmic entity. This would mean that dark matter's gravitational pull and dark energy's repulsive force could be connected by a deeper, as yet unknown principle of physics. While such ideas are speculative, they present an exciting possibility for future research, that dark matter and dark energy, though seemingly opposites, could actually be linked at a more fundamental level. If they are indeed connected, uncovering the true nature of this connection could not only explain the role each plays in shaping the universe, but could also lead to new breakthroughs in physics. These kinds of unified theories are especially appealing because they could offer a more complete and elegant description of the universe, linking together the very forces that govern all of existence. However, dark matter's role in shaping the universe seems more straightforward. It's the mysterious substance that makes up about 25% of the universe's mass-energy content. Yet, we can't see it. Its existence is inferred through its gravitational effects on visible matter. Without dark matter, galaxies would not have enough mass to stay intact. The stars in a galaxy should, based on their movement, be flying apart, but they don't. This is where dark matter's gravitational influence comes in. It provides the extra mass needed to hold galaxies together. Without dark matter, the formation of galaxies and the large-scale structure of the universe as we know it would not be possible. On the other hand, dark energy works in the opposite direction. Instead of binding objects together, it accelerates their separation. Dark energy is thought to make up about 70% of the universe's mass energy content, and it is responsible for the ever-increasing rate of expansion of space itself. Where dark matter clumps together, helping to form galaxies, dark energy pushes everything apart. It's a force that operates on the largest scales of the universe, shaping the overall geometry of space-time and determining the universe's ultimate fate. Yet, while dark matter's role in galaxy formation and structure is clear, dark energy remains elusive. We understand that it's responsible for the accelerated expansion of the universe, but its true nature is still one of the biggest mysteries in cosmology. Some researchers, like David Bohm, a quantum physicist known for his work on quantum theory, have proposed that the universe operates as a holistic system, where dark matter and dark energy are not separate phenomena, but rather two aspects of the same cosmic framework. According to Bohm's holistic quantum theory, the universe's apparent randomness could be the result of a deeper, hidden order that governs both dark matter and dark energy. This theory suggests that both of these forces are part of a larger interconnected system that we have yet to fully understand. Bohm's approach challenges the standard view that dark matter and dark energy are simply separate components of the universe. Instead, he suggests that they might be two sides of the same coin, shaped by a deeper underlying structure of the cosmos. This idea adds another layer of complexity to our understanding of the universe's fundamental forces, and it raises the possibility that the key to understanding dark energy and dark matter lies in the unification of quantum mechanics and gravity. As we continue to probe the mysteries of dark energy and dark matter, the question of how these two phenomena interact remains an open one. Are they truly separate forces, or are they manifestations of a deeper, unified principle? While we have made tremendous progress in understanding the role of dark matter in shaping the structure of the universe, dark energy still holds many secrets. Could these two forces be tied together in a way we have yet to imagine? Could the forces that govern the large-scale structure of the universe be part of a larger, interconnected system of cosmic forces? These are questions that continue to drive scientific inquiry. In the coming years, new experiments and observations will undoubtedly shed more light on the relationship between dark energy and dark matter. Missions like the Dark Energy Survey, the Euclid mission, and others will provide more precise measurements of the universe's expansion and the distribution of galaxies, helping to refine our understanding of dark energy and its role in shaping the cosmos. As we gather more data, we may find that the answer lies not in understanding these phenomena as separate entities, but in uncovering the deeper connections between them. For now, the mysteries of dark energy and dark matter remain at the forefront of cosmological research, and the more we learn, the closer we get to understanding the forces that govern the universe on the grandest scales. Whether they are separate or connected, the interplay between dark energy and dark matter will ultimately provide the key to unlocking the most fundamental secrets of the cosmos, and with each new discovery, we move one step closer to understanding the true nature of the universe itself. One of the most profound challenges in modern physics is unifying the three fundamental pillars of our understanding of the universe: quantum mechanics, gravity, and cosmology. These three fields have each revolutionized our understanding of the universe, but they have always seemed at odds with each other, operating in vastly different realms of the cosmos. Quantum mechanics governs the behavior of particles at the tiniest scales. Gravity dictates the behavior of massive objects and the very structure of space-time itself, and cosmology is the science of the universe on the larger scales. Each field has its own set of laws, but for many years we've struggled to reconcile them into a single, unified framework. Dark energy, the mysterious force responsible for the accelerated expansion of the universe, may hold the key to unlocking this unified theory. If we can understand how dark energy influences space-time on both the quantum and cosmic scales, we might be able to weave together quantum mechanics, gravity, and cosmology into a single, cohesive theory that explains the fundamental workings of the universe. Cecilia J. McCarty, a physicist known for her work on quantum loop gravity, offers one possible path toward this unification. Quantum loop gravity is an attempt to quantize gravity, merging the principles of quantum mechanics with Einstein's theory of general relativity. One of the key challenges of unifying quantum mechanics and gravity has been the way they deal with the fabric of space-time. While quantum mechanics operates on the scale of subatomic particles, general relativity deals with the large-scale curvature of space-time, making it difficult to reconcile the two. McCarty's work with quantum loop gravity seeks to explain gravity in terms of discrete, quantized chunks, much like how we think about particles in quantum mechanics. In this framework, space-time itself is made up of tiny, indivisible loops or quanta of space. These loops would allow gravity to be treated like a quantum field, similar to how electromagnetic forces are understood in quantum electrodynamics. If dark energy is an inherent part of the fabric of space-time, as many theorists believe, quantum loop gravity could potentially incorporate it into a unified framework, offering a new understanding of how the universe operates on both the smallest and largest scales. In addition to McCarty's approach, Hermann Nicolai, a leading researcher in the field of quantum cosmology, has developed his own theories that aim to unify the forces of nature. Nicolai's work explores how the fundamental forces, including gravity and the quantum forces that govern particle behavior, might be derived from a single underlying theory. One of the key ideas in Nicolai's research is the concept of supersymmetry, a theoretical framework that proposes that each particle in the Standard Model has a partner particle with different properties. Supersymmetry could help explain why the fundamental forces are so different in strength and nature, and it might also offer insights into the relationship between dark energy, gravity, and quantum mechanics. Nicolai's approach suggests that the universe's expansion, driven by dark energy, could be explained as the result of a more fundamental underlying symmetry in nature, a symmetry that connects the behavior of particles at the smallest scales with the large-scale structure of the cosmos. By unifying the forces of nature, Nicolai's theory could provide a more complete understanding of how dark energy fits into the larger picture of cosmic evolution. Another scientist whose work has contributed to the search for a unified theory of everything is John Archibald Wheeler. Wheeler's ideas on space-time and the fundamental nature of the universe have had a lasting impact on modern physics. He is perhaps best known for coining the phrase black hole, and for his work on the concept of the fabric of space-time. Wheeler believed that space-time itself was not a static backdrop, but rather a dynamic entity that could be shaped by the presence of energy and matter. This idea aligns closely with our modern understanding of general relativity, which shows that mass and energy warp space-time, creating the gravitational fields we observe. Wheeler's insights also suggest that dark energy, as a force that affects the expansion of the universe, could be seen as an extension of this dynamic view of space-time. Just as matter bends and shapes space-time, dark energy could be influencing the geometry of space on a cosmic scale. By integrating dark energy into the fabric of space-time, Wheeler's ideas could provide a framework for understanding how both dark energy and dark matter interact with the universe's large-scale structure. These ideas set the stage for the development of a truly unified theory of everything, one that could reconcile the forces of nature and provide a deeper understanding of dark energy's role in shaping the cosmos. If dark energy is tied to the very structure of space-time itself, it could be a manifestation of the same underlying principles that govern both gravity and quantum mechanics. The search for this unification is ongoing, and scientists like McCarty, Nicolai, and Wheeler are working to bring us closer to a comprehensive theory that explains not just dark energy, but the entire universe. While these theories offer exciting possibilities, they also raise profound questions about the nature of the universe. What is the true relationship between dark energy, dark matter, and the fabric of space-time? How do quantum mechanics and gravity fit together, and can we find a way to unify them under a single framework? These questions are not just abstract puzzles. They are crucial for understanding the fundamental laws that govern the universe. The answers we seek may ultimately lie in a unified theory that brings together all the forces of nature, offering a complete description of the universe from the smallest particles to the largest cosmic structures. As we continue our exploration of dark energy and its role in the universe, we must also consider the philosophical implications of its existence. Dark energy challenges our basic assumptions about the nature of reality, pushing us to rethink our understanding of space, time, and the forces that govern the universe. As we delve deeper into the mysteries of dark energy, we are not just uncovering the secrets of the cosmos, we're also confronting the limits of human knowledge and the boundaries of scientific inquiry. The search for a unified theory of everything is not just a quest for answers, it is a journey into the very heart of the universe, where the fundamental truths of existence await discovery. As we venture deeper into the mysteries of dark energy, we find ourselves confronted with not just scientific questions, but profound philosophical ones as well. Dark energy, with its mysterious effects on the expansion of the universe, challenges our very understanding of reality. It forces us to rethink the nature of space, time, and the forces that shape our existence. The more we learn about dark energy, the more we realize that it is not just a cosmic phenomenon, but a concept that touches on the deepest questions of philosophy and existence itself. For centuries, thinkers have pondered the nature of the universe, and many of the questions raised by modern science were already being considered by early philosophers. One such philosopher was Immanuel Kant, who, in the late 18th century, proposed a radical idea about how we perceive the universe. Kant argued that our understanding of the world is shaped by the way our minds organize sensory information. In his view, space and time are not objective, external realities, but rather forms of perception through which we experience the world. According to Kant, the universe itself is unknowable beyond our perception of it. In a way, Kant's ideas suggest that the very fabric of reality is shaped by the way we interact with it. Now, when we look at dark energy, we can't help but think about Kant's view of space and time. If dark energy is indeed a force that is affecting the very structure of the universe, pushing galaxies apart at an accelerating rate, it raises the question, is this acceleration something objective, or is it a phenomenon shaped by our perception of space and time? Could dark energy, in some way, be a reflection of our mind's interaction with the universe? This is, of course, an idea that will require much more evidence to explore, but it reminds us of Kant's crucial insight, that our understanding of reality may be shaped by more than just objective observations. Later, in the early 20th century, Arthur Eddington, an English astrophysicist, explored a different aspect of this question, the relationship between the universe's physical properties and the nature of reality itself. Eddington was fascinated by the idea that the universe might have an underlying unity, a deeper structure that connects everything together. He argued that the physical universe we observe is just a manifestation of deeper, more fundamental principles that are not immediately accessible to us. Eddington's perspective on the universe's interconnectedness resonates with the questions raised by dark energy. If dark energy is shaping the expansion of the universe, is it simply a force that we can measure and describe, or is it a deeper manifestation of some fundamental interconnected reality that we are still struggling to understand? Brian Greene, a modern theoretical physicist, has also weighed in on the philosophical implications of cosmology. Greene's work on string theory and the multiverse has led him to a fascinating perspective on the nature of existence. He argues that cosmology, the study of the universe, can be a powerful tool in understanding the ultimate nature of reality. According to Greene, our universe may not be the only one. String theory suggests the possibility of a multiverse, a collection of universes, each with its own laws of physics. In this framework, dark energy could be just one force among many, shaping not just our universe, but potentially many others. Greene's ideas push us to think about dark energy in a broader, more abstract way, as something that might not just define the fate of our universe, but could also be part of a larger cosmic system, influencing countless universes in a way we have yet to understand. These ideas take us even further into the realm of deep, interconnected forces. But perhaps one of the most intriguing perspectives comes from David Bohm, a quantum physicist who proposed a radically different way of thinking about the universe. Bohm's theory of the holistic universe suggests that the universe is not made up of separate, independent parts, but is instead a deeply interconnected whole. In his view, everything in the universe, every particle, every force, every phenomenon, is part of a larger unified system. According to Bohm, the apparent separateness of objects in the universe is an illusion. In reality, everything is connected in ways we cannot yet fully perceive. Dark energy, in this context, could be seen as a manifestation of this deeper, holistic connection, an expression of the underlying unity of the cosmos. Instead of being a force acting on the universe from the outside, dark energy might be an inherent part of the universe's fabric, reflecting the deep interconnectedness of all things. Bohm's holistic view challenges the way we traditionally think about the universe. Instead of viewing dark energy as just a force that pushes galaxies apart, we might consider it as part of a larger, more complex system that shapes the entire cosmos. In this sense, dark energy could represent not just a force of repulsion, but a force that embodies the unity of the universe itself. This view suggests that dark energy might be a key to understanding the deeper structure of space-time, linking the quantum world with the vast, expanding universe. As we explore the philosophical implications of dark energy, we are confronted with the idea that our understanding of the universe might need to be reimagined. Dark energy is not just a cosmic phenomenon, it challenges our fundamental concepts of space, time, and reality. If dark energy is indeed influencing the expansion of the universe, it forces us to rethink what we know about the nature of space-time and the forces that govern it. It may even require us to reconsider the very way we perceive the universe and our place within it. Could dark energy be more than just a force pushing galaxies apart? Could it be a manifestation of a deeper, interconnected reality that we have yet to understand? As we move forward in our search for answers, we will continue to confront these profound questions about the nature of existence. Dark energy is a force that might hold the key to unlocking some of the deepest mysteries of the cosmos, and in doing so, it might change our understanding of reality itself. The more we explore the nature of dark energy, the more we find ourselves asking questions that go beyond the realm of science. These questions touch on the very essence of existence, forcing us to think about the universe in ways we have never done before. As we continue our journey through the cosmos, we must remain open to new possibilities, knowing that dark energy, with all its mysteries, may hold the answers to some of the most fundamental questions about the nature of the universe and the reality we live in. The discovery of dark energy has not only transformed our understanding of the universe's expansion, but also has profound implications for how we think about the very fabric of space-time. For centuries, space and time were considered static and unchanging, the unyielding stage upon which the events of the cosmos unfolded. However, with the advent of Einstein's theories of relativity in the early 20th century, space and time were revealed to be much more dynamic and malleable than previously imagined. Now, dark energy, an unseen force pushing galaxies apart at an accelerating rate, may be challenging the very nature of space-time itself, potentially altering how we understand the universe's most fundamental structures. At the heart of this revolution in thinking is Albert Einstein's theory of general relativity, which radically transformed how we view gravity and the geometry of space-time. According to general relativity, space and time are not separate entities, but rather form a single four-dimensional fabric known as space-time. Massive objects like stars and planets warp this fabric, and what we perceive as gravity is simply the result of objects following the curved paths in space-time created by this warping. This understanding has allowed scientists to predict phenomena such as the bending of light around massive objects and the time dilation experienced near black holes, which have been confirmed by numerous observations. But dark energy presents a new challenge. While general relativity beautifully explains how mass and energy curve space-time, dark energy seems to do the opposite. It stretches space-time, accelerating the expansion of the universe itself. As galaxies move further apart, dark energy's influence grows stronger, effectively driving the cosmic acceleration. In this sense, dark energy is tied to the geometry of space-time in a way that pushes our understanding beyond the traditional concepts of gravity and curvature. Einstein's equations predicted that the universe could either be static, expanding, or contracting, depending on the amount of mass and energy in the universe. But in the early 20th century, when astronomers realized that the universe was expanding, it led Einstein to introduce his cosmological constant, a term he added to his equations to allow for a static universe. Once the expansion was confirmed, Einstein abandoned the cosmological constant, calling it his greatest blunder. However, in the 1990s, after the discovery that the expansion of the universe is accelerating, the cosmological constant made a dramatic comeback, now understood as the mathematical representation of dark energy. The challenge we face today is understanding how this mysterious force is connected to the curvature of space-time in a meaningful way. The influence of dark energy on space-time raises even deeper questions. If dark energy is indeed altering the geometry of the universe, could it also be affecting the nature of time itself? This is a question raised by Lee Smolin, a physicist whose work has focused on the nature of time and cosmology. Smolin's ideas challenge our conventional understanding of time as a constant linear progression. Instead, he suggests that time might not be an absolute and unchanging backdrop to the universe. According to Smolin, the passage of time itself might be shaped by the universe's evolution. In his view, the laws of physics may evolve over time, with time itself being an emergent property of the universe. Smolin's ideas imply that dark energy, as a dynamic force pushing the universe apart, could be fundamentally connected to the way time behaves. If dark energy is influencing the expansion of space-time, then time itself might not be the fixed, uniform experience that we assume it to be. Instead, it could be a malleable quantity that is shaped by the expansion of the universe, with dark energy playing a crucial role in that evolution. This perspective forces us to reconsider not just how the universe is expanding, but how we experience time as part of the ever-changing fabric of space-time. Building on this idea of a dynamic, evolving universe, Juan Maldacena, a theoretical physicist best known for his work on string theory, has proposed the holographic principle, which offers a different way of thinking about the relationship between space-time and the forces that govern it. Maldacena's principle suggests that the entire universe, including space-time itself, might be a projection from a lower dimensional boundary. In essence, all the information about the universe we observe could be encoded on a distant boundary, much like the information on a hologram appears to be three-dimensional, even though it is encoded on a two-dimensional surface. In the context of dark energy, the holographic principle offers a novel way of thinking about how dark energy might influence the geometry of space-time. If the universe is a projection, then the accelerating expansion caused by dark energy could be a result of how the universe's information is encoded on this lower dimensional boundary. Dark energy could thus be understood as a force that emerges from the higher dimensional structure of space-time, offering a new lens through which we might understand its role in the universe. This approach connects the large-scale structure of the cosmos with the fundamental principles of quantum mechanics, providing a bridge between the small and large scales of the universe. These theories, all of them fascinating in their own right, suggest that dark energy is not just a force acting on the universe from the outside. It is deeply tied to the fundamental nature of space-time, shaping its geometry and perhaps even influencing the flow of time itself. If dark energy is altering space-time in such fundamental ways, it could represent a doorway to understanding the deepest mysteries of the cosmos, including the true nature of time, space, and reality. But beyond the theoretical implications, the study of dark energy also forces us to confront deeper philosophical questions about the nature of existence. If the expansion of the universe is being driven by dark energy, how does that affect our understanding of the universe's beginning and end? Are we living in a universe that is simply stretching forever, growing colder and emptier as time goes on, or is there more to the story? What does it mean for us as conscious beings to live in a universe that is constantly changing? A universe where space and time themselves are not static but dynamic forces, influenced by unseen energies. As we move forward in our exploration of dark energy, we must consider how it could fundamentally alter our understanding of reality itself. Could the universe's accelerating expansion, driven by dark energy, be the key to unlocking a deeper understanding of the forces that govern existence? The implications of dark energy stretch far beyond the realm of physics, touching on the very nature of time, space, and reality. As we continue to probe its mysteries, we might find that the answers we seek lie not just in understanding dark energy, but in understanding how the very fabric of the universe is woven together. In the next phase of our exploration, we will continue to dive into the unknown, pushing the boundaries of what we know about dark energy and its role in shaping the cosmos. The deeper we look, the more we realize that the universe is not just a collection of stars and galaxies, it is a living, evolving entity, shaped by forces both seen and unseen. Dark energy may hold the key to understanding this dynamic, ever-changing universe, and with each new discovery, we get one step closer to understanding the true nature of reality itself. As we look toward the future of dark energy research, one thing is clear. The next few decades hold the potential for groundbreaking discoveries that could radically change our understanding of the universe. Scientists are eager to answer the many questions that remain about this mysterious force and its role in the evolution of the cosmos. What exactly is dark energy? How does it interact with the other fundamental forces of nature? What does its continued influence mean for the fate of the universe? As our tools and techniques become more advanced, we are poised to make new strides in answering these questions and uncovering dark energy's secrets. One of the most exciting developments on the horizon is the next generation of telescopes, missions, and observatories that will allow us to probe the universe in ways that were once unimaginable. One such project is the Large Synoptic Survey Telescope, or LSST, currently under construction in Chile. Once operational, the LSST will map the entire sky every few days, collecting data on billions of stars, galaxies, and other cosmic phenomena. With its unprecedented ability to observe the universe in detail, the LSST will provide valuable information on the expansion of the universe and the role of dark energy in that process. By observing the distribution of galaxies and their movements, scientists will be able to track how dark energy is affecting the universe's acceleration, offering insights that could refine or challenge current models. Another major project that will significantly contribute to our understanding of dark energy is the Square Kilometre Array, or SKA. The SKA is an ambitious radio telescope project that will be built in both Australia and South Africa. When completed, it will be the largest radio telescope in the world, capable of mapping the universe with incredible precision. One of the key goals of the SKA is to measure the effects of dark energy on the large-scale structure of the universe. By studying the distribution of galaxies, the cosmic microwave background and other phenomena, the SKA will provide crucial data on how dark energy has influenced the universe's expansion over cosmic time. With its advanced capabilities, the SKA will also help test theories of gravity and space-time, offering new insights into the role of dark energy in shaping the cosmos. These missions, along with other observatories like the James Webb Space Telescope and Euclid, will form a new generation of tools that will provide a much deeper understanding of dark energy's properties. As we collect more precise data, scientists will be able to test existing theories, refine our models, and potentially uncover entirely new phenomena related to dark energy. In addition to these observational missions, there are also several theoretical advancements that could help us unlock the mysteries of dark energy. One area of research that has garnered significant attention in recent years is the field of quantum gravity. Quantum gravity seeks to reconcile two of the most successful theories in physics, quantum mechanics and general relativity, which describe the universe at the smallest and largest scales, respectively. While both theories have been extremely successful in their own domains, they have not yet been unified into a single framework. Quantum gravity has the potential to explain how the forces of nature, including dark energy, interact on both the quantum and cosmic scales. Scientists like Carlo Rovelli and Lee Smolin have been working on theories of quantum gravity that could provide a better understanding of how dark energy fits into the fabric of space-time. Some theories suggest that dark energy could be a manifestation of quantum fluctuations in the vacuum, while others propose that it might be related to the properties of space-time itself. By studying quantum gravity and dark energy together, we may be able to uncover the deeper connections between the fundamental forces of nature and develop a unified theory of everything that explains both the micro and macro scales of the universe. Another exciting area of research is string theory, which proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings. String theory has the potential to explain the fundamental forces of nature, including gravity and dark energy, within a single framework. Some models of string theory suggest that dark energy could arise from the interactions of these strings in higher dimensional space. If string theory can be experimentally verified, it could offer a powerful explanation for the nature of dark energy and its role in the evolution of the universe. As we continue to advance our understanding of quantum gravity and string theory, the potential for breakthroughs in dark energy research grows. These theories offer a new way of thinking about the universe, one that could ultimately lead to a deeper understanding of the forces that govern reality. However, it's important to recognize that these ideas are still in their early stages, and much work remains to be done before we can fully comprehend the nature of dark energy and its implications. The next few decades will undoubtedly bring new discoveries that will reshape our understanding of dark energy and the universe as a whole. As our observational tools become more sophisticated, and as new theoretical frameworks are developed, we will gain deeper insights into the mysteries of the cosmos. Dark energy, with its vast influence on the universe's expansion, will continue to be a central focus of research. Whether it is ultimately understood as a force that drives the universe apart or as a manifestation of a deeper, more fundamental principle, dark energy's role in shaping the fate of the cosmos cannot be overstated. As we look to the future, the question of dark energy's ultimate origin and its true nature remains open. New experiments such as those being conducted with the LSST and SKA will help refine our understanding of its properties, while theoretical breakthroughs in quantum gravity and string theory could provide the key to unifying dark energy with the other forces of nature. With each new discovery, we move closer to unlocking the deepest secrets of the universe and understanding the forces that govern it. In the end, the future of dark energy research is not just about answering one question, but about transforming our entire understanding of the universe itself. The mysteries of dark energy are intertwined with the very fabric of space-time, and as we continue to unravel these mysteries, we will gain new insights into the nature of reality and the cosmic forces that shape our existence. The journey of discovery is far from over, and the answers we seek will not only reveal the nature of dark energy, but will also provide the key to understanding the fundamental structure of the cosmos. Dark energy is the great cosmic force that shapes the very future of the universe. It's responsible for the accelerating expansion of space pushing galaxies further apart with each passing moment. And as we continue to study this mysterious energy, we're faced with some profound questions about its role in the larger evolution of the cosmos. What does it mean for the universe's ultimate fate? How does dark energy fit into the life cycle of the universe itself, from its birth to its potential end? These are questions that not only challenge our understanding of the universe, but also stretch the boundaries of science and philosophy. At present, dark energy makes up about 70% of the total energy content of the universe, yet its exact nature is still elusive. This dominance is a stark reminder of how central dark energy is to the structure of the cosmos. It affects the geometry of space-time itself, influencing everything from the large-scale distribution of galaxies to the ultimate fate of the universe. Without dark energy, the expansion of the universe would likely be slowing down, as gravity would eventually overcome the outward push of the expansion. Instead, dark energy continues to drive the universe apart, accelerating the expansion at a rate that is increasing over time. This acceleration hints at a dramatic, far-reaching role for dark energy in the evolution of the cosmos. Some theories suggest that dark energy is not just a force pushing galaxies apart, but a key player in shaping the entire life cycle of the universe. The question of whether dark energy will continue to drive this expansion, leading to an ever-growing, increasingly empty universe, or whether it will eventually reverse course, is central to debates about the universe's long-term future. One possibility, often referred to as the Big Freeze, envisions a universe that expands forever under the influence of dark energy. In this scenario, galaxies, stars, and other cosmic structures would continue to drift farther and farther apart. As time passes, the universe would grow colder and darker, with fewer stars and galaxies visible. Eventually, stars would burn out, and black holes would dominate the cosmic landscape. The universe would become increasingly isolated, with galaxies beyond our observational reach. In this cold, dark future, the cosmos would reach a state of entropy, where no new energy or matter could emerge, marking the end of active cosmic processes. However, there are other theories that paint a very different picture for the universe's future. For instance, some physicists propose that dark energy could evolve over time. If dark energy becomes stronger in the future, it could eventually rip apart galaxies, stars, planets, and even atoms in a cataclysmic event known as the Big Rip. In this scenario, the universe's expansion would accelerate to such a degree that even the gravitational forces holding galaxies and stars together would be overcome by dark energy. The fabric of space-time itself could tear apart, creating a dramatic and violent end to the cosmos. These two potential outcomes, the Big Freeze and the Big Rip, are just two of many possibilities that have been proposed. As we continue to gather data and refine our models of dark energy, more ideas will emerge, each with its own predictions for the ultimate fate of the universe. What's clear, however, is that dark energy will play a crucial role in shaping the outcome. It is quite literally the force that holds the future of the universe in its hands. As we look ahead, it's important to consider how the study of dark energy will continue to evolve. Over the next few decades, new technologies and experiments will give us a much clearer picture of dark energy's properties and its role in cosmic evolution. Missions like the James Webb Space Telescope and Euclid will provide unprecedented views of the distant universe, allowing scientists to map the distribution of galaxies and supernovae with greater precision. These observations will help us refine our understanding of the expansion of the universe, providing valuable data on how dark energy has shaped its evolution over time. The Square Kilometre Array and LSST will also contribute to this effort, providing new insights into the large-scale structure of the universe and how dark energy influences the cosmic web. By measuring the redshifts of galaxies and other cosmic objects, these experiments will help test our models of cosmic acceleration and dark energy, and may even uncover new phenomena that challenge our current understanding. As dark energy continues to reveal its secrets, it's likely that new theoretical frameworks will emerge to explain its nature. The unification of quantum mechanics and general relativity, through theories like quantum gravity and string theory, may provide a deeper understanding of how dark energy interacts with space-time. If dark energy is indeed connected to the fabric of space-time itself, as many researchers suspect, then breakthroughs in these fields could unlock new insights into the fundamental structure of the universe. The future of dark energy research also raises important questions about the very nature of existence itself. As we uncover more about this mysterious force, we may find that dark energy offers a window into understanding the ultimate nature of the cosmos. Is dark energy a fundamental property of the universe, or is it a byproduct of some deeper, more fundamental principle? Is it tied to the birth of the universe, and could it help explain its eventual end? These are questions that lie at the heart of cosmology, and as dark energy research progresses, they will continue to drive our quest for answers. But beyond the scientific implications, dark energy also has a broader cultural significance. It challenges our deepest assumptions about the universe and forces us to confront the possibility that the cosmos is far more complex than we ever imagined. The study of dark energy is not just a scientific pursuit, it is a philosophical one, as it touches on questions of existence, the nature of time and space, and the future of all things. As we move forward, the discoveries we make will not only shape our understanding of the universe, but also transform our place in it. Ultimately, the mystery of dark energy remains one of the greatest challenges in modern science. It has the power to reshape our understanding of the cosmos, from its beginning to its end, and offer new insights into the forces that govern reality. While we have come a long way in our exploration of dark energy, the journey is far from over. The answers we seek may be closer than we think, but they are still shrouded in mystery, waiting to be uncovered by the next generation of scientists. As we continue to explore the cosmos, we will undoubtedly find new clues that will guide us toward a deeper understanding of the universe and its ultimate fate. Throughout this journey into the world of dark energy, we've explored some of the most profound questions in modern science. We've looked at how dark energy is driving the accelerated expansion of the universe, challenging our understanding of space-time and the forces that govern the cosmos. From its relationship with gravity and quantum mechanics to its potential role in shaping the universe's ultimate fate, dark energy has emerged as a central force in cosmology. Yet, despite decades of research and observation, it remains one of the greatest mysteries in science. We've discussed how dark energy makes up a staggering 70% of the universe's energy content, yet we still don't fully understand what it is. We've looked at the ongoing debate about whether it's a constant force, as originally suggested by Einstein's cosmological constant, or whether it's something more dynamic, like the concept of quintessence. Alongside this, we've considered alternative ideas, such as the possibility that dark energy is tied to quantum fluctuations in the vacuum or even the fabric of space-time itself. What we do know for certain is that dark energy has a profound effect on the universe, influencing its expansion in ways we're only beginning to understand. Along the way, we've also explored the philosophical and existential implications of dark energy. It forces us to rethink fundamental concepts about space, time, and reality. Can dark energy be the key to unifying quantum mechanics, gravity, and cosmology? Could it be part of a deeper, more interconnected structure of the universe, as suggested by scientists like David Bohm and Lee Smolin? And perhaps most importantly, what does dark energy tell us about the future of the universe and our place within it? Despite the many theories and models, the true nature of dark energy remains elusive. It is a force that shapes the cosmos, yet its origins and its behavior are still hidden from view. But as we continue to gather more data through advanced telescopes, observatories, and theoretical breakthroughs, we move closer to unlocking the secrets of dark energy. Every new discovery brings us one step closer to understanding how the universe works and where it's headed. The study of dark energy is an exciting and ever-evolving field that continues to push the boundaries of scientific inquiry. While much remains unknown, the quest to understand dark energy will undoubtedly continue to drive research and exploration in the coming decades. Each new piece of data, every theoretical breakthrough, and each mission into the farthest reaches of space will bring us closer to a more complete understanding of the cosmos. In the end, dark energy is a reminder of how vast and mysterious the universe truly is. It challenges us to think bigger, to look deeper, and to ask questions that go beyond the boundaries of what we currently know. And while we may not have all the answers yet, it's that curiosity, that drive to understand the unknown, that will continue to propel us forward. With every discovery, we come closer to uncovering the fundamental truths of existence and our place within the infinite cosmos.